Hi guys, Mathologic here. Today we're going to be taking a mathematical look at the immense power of course, the Bugatti Chiron. There's really 5 formulas we're going to be using here to calculate the power. We're going to be looking at the power of the Bugatti Chiron. Of course, that enormous W16 8 litre quad turbocharged, that iconic Bugatti engine. So the 5 formulas we're going to be using are some physics formulas. Work equals force multiplied by displacement. Now, all the other formulas are kind of used to branch into this. So to calculate work, we're going to be extrapolating this and looking at power, and that's how we're going to eventually calculate the power of the Bugatti Chiron, which is energy divided by time. Force, going to be using acceleration as V minus U on T, and then of course using that for force equals ma, good old second law of motion. And then displacement, we're going to be using S equals half AT squared plus UT. And this is really all we need to be able to quantify the power brought about by that enormous engine. So before we start, a few data points we need to write down. So we know the mass of the car is 1,977 kilograms. It's a heavy car. 0 to 100 kilometers per hour, which is the period we're going to be using to calculate the engine's power. Of course, you could do beyond this, but I think it's a good point to really measure the maximal power without, getting into things like air resistance too much, which of course are at play. But I think the best kind of basic response to this will be looking at 0 to 100 kilometers per hour. Anyway, that's going to be 2.4 seconds. And then friction coefficient of the car is going to be 0.38. I just found this on the internet. In the basic mode that the car accelerates in, the friction coefficient of this car is 0.38. I assume that includes tyres, wind resistance, everything has been measured there. So to start, we're going to, let's just convert 0 to 100 kilometers per hour into meters per second, because that's really what we're going to be using here. So we can say 0 to 27.78 meters per second. It's the same thing, just divide this by 3.6. And then to calculate acceleration, I'm going to be using V minus U. So our ending velocity is 27.78 minus, and then of course starting from standstill and divided by the lightning fast, 2.4 seconds. And that's going to give us an acceleration of 11.575 meters per second squared, which you might notice is actually more than gravity. So if you do have the privilege of going in the sky, you will feel more than 1g accelerating, which is an interesting side note. Okay, second step. We're going to be looking at the displacement of the car over this time using S equals half AT squared plus UT. This is just going to cancel out because initial speed is 0. So we're going to get half multiplied by 11.575 multiplied by 2.4 squared. And that's going to give us tiny distance, 33.34 meters, which you imagine if you look at a 100 meter running track, you're only really going to reach a third of that before the car's already at 100 kilometers per hour, which is insane. So we've calculated S. We now just need to look at F. So we'll go back to here, step 3. This is going to equal out S. So we've calculated that. We'll come back and use this later. So we know force equals ma. I'm going to refine this a bit. We're going to say the coefficient of the net force equals the driving force. So that means that there is a coefficient taken off all the force that is being provided by the engine. Some of that is being wasted due to the air and the tyres and heat and everything. So if we do our 0.38 multiplied by F, this should be the driving force, by the way, and that's what we're going to be using to calculate power, is equal to 1977 multiplied by 11.575, and we're going to get the driving force is going to be 22,884 newtons divided by 0.38, and that's going to give us our engine providing 60,220 newtons, which, if you think about it, that is a lot of force. Now, to put this in energy forms, we're going to have to use this work equals force multiplied by displacement. So I'll get another sheet here. So work equals force multiplied by displacement. We know displacement equals 33.34 meters, which is essentially, as I said, the third of the 100-meter sprint. And then, of course, force is going to be 60,220 newtons. So the total work in joules is going to be 60,220 multiplied by 33.34, which is going to give us 2,007,735 joules, which is a lot of energy. And then, of course, to calculate power, we're going to do energy divided by time. So 2,007,735 divided by, of course, 2.4 seconds, in which it is all dispersed, so to speak. And that is going to give us 836,456 watts, or in the automotive world, we really do kilowatts. So there you go, 836.4 kilowatts. So we've got our number, 836.4 kilowatts. But you'll notice if we do a bit of our own research here, going on Bugatti's buzzword-filled website and accept the cookies. So here we've got 1500 horsepower and a lovely little diagram of the engine. So if we do a quick horsepower to kilowatt conversion, and we put in 1500 horsepower, we get just over 1100 kilowatts. So you might be asking, what's happened here? Like, we've calculated it to be 836 kilowatts. And the truth is, this 1500 kilowatts is really only achieved when the engine is revving to its maximum sort of potential, and up until that it is a linear increase. So you haven't got a constant power output. It is dependent on the revs of the engine. So I'd imagine if you did look at a chart of power to revs, you would see that sort of the median position over that 100 kilometer per hour point, maybe 1, 2, 3 gears, your median position would be around 836 kilowatts. That's it for this video, guys. Thanks very much for watching. See you on the next one.